Alright guys, so this is part 2 of area ratios, and this problem on the bottom of your paper should be kind of a simple one if you get the hang of it. It says if you shrink a circle's diameter to a third of its original size, here's a scale drawing of the original circle, and then now it's a third of its original diameter. What is the perimeter and area ratio comparing the original to the new? So, read that again to yourself, maybe pause that, try it on your own if you think you get it. If not, just follow along here. So, the original diameter is some value x, and the new one is 3x. Most people who don't have a lot of math knowledge will just say, oh, it's a 1:3 ratio in terms of perimeter or circumference, and it's probably a 1:3 ratio in terms of area. That is true, for the perimeter. It is a 3:1 scale, but it's not true for the area. And you can kind of see it visually. Clearly way more than 3 of these circles would fit inside that. If you think of area being space, way more than 3 of those would fit inside there. Think about how many of these circles would fit inside here. And like I said before, this is a scale drawing of circles with a 3:1 ratio for diameter. And hopefully you realize it's 9 of those circles that would fit inside there. And again, that comes from the scale factor. If these are similar figures, it's a scale factor squared. So it's a 9, and then 1 squared is 1, a 9:1 ratio. So it should be kind of obvious if you understand, we did pi r squared the other day. If you square the radius, if you square the diameter, yeah, I said it right. If you square the radius, and you're squaring a value that's 3 times bigger, 3 times 3, of course, is 9. This area is going to be 9 times as big. So hopefully that makes sense visually as well as in terms of the actual rule we talked about. On the back of your page is kind of a tricky problem. Talks about this quadrilateral. It's got side lengths 5, 3, 7, and 6 inches in length. It's got a given area of 18 square inches. And there's another quadrilateral, which, key word in here is that it's similar to the first quadrilateral with an area of 50 square inches. Find each side length, basically, of the bigger quadrilateral. So read that to yourself, try that on your own. This took about 6 minutes in class. This was kind of a lengthy problem in terms of the steps involved. You may want to pause it, try it on your own. The entry into this problem is a little tricky. The entry into this problem is not a scale factor. You're usually thinking, oh, what's a scale factor? I'm going to work from the scale factor. In this problem, the entry is actually the 2 different areas. Give you an area of 18 and give you an area of 50. You've got to work from the area ratio and work backwards. So think about how you work backwards. Usually if you have a scale factor, you square it to get to here. If you're working backwards, you take a square root. Now if you take the square root of both of these, you kind of get messy square roots. Something you might want to do first is reduce this ratio. Think about what goes into both of these and divide that common factor out. So if you divide this by 2, you get 25. If you divide this by 2, you get 9, which is still the same ratio, but it's a much more manageable ratio in terms of working backwards. Work backwards from this, you take the square root of both of these, and you get a pretty simple 3:5 ratio. Square root of this is 3, square root of this is 5. In other words, each one of these side lengths are 3/5 of the bigger one. And if you want to flip that over and work backwards, each one of the new sides we're trying to find are 5/3, or 1.66667 times larger than the given one. So you could take all of these, multiply each one of them by 1.66667, or 1 2/3, or you can call that 5/3, and you get the new lengths on there. You can also do it with proportions. You could say 3 is to 5 as 5 is to x, or 3 is to 5 as 6 is to x, and solve for the missing pieces on there. Traditionally I would do this with proportions. This is doing it with sort of a multiplier in there. So you should get 8 1/3. Again, if you want to pause it here and try to calculate all 3 of those remaining sides, you should end up with 8 1/3, 5 inches, 11 2/3, and then of course one of them is 10 inches. Hopefully that makes sense. But again, that's a 5-6 minute problem in class that we did. It was kind of a tricky one. So here's where we get into the ones that are kind of the meat and potatoes of this section. This is kind of the big thing I think you should understand on here. To save you some writing, instead of labeling all the corners with letters, just label this region 1, that's a Roman numeral 1, and region 2, Roman numeral 2. I'm going to add in some arrows on here. These lines are parallel, so I just threw some arrows on there. And the second thing is these two side lengths are congruent. Given you got a right angle box in the corner down here, which hopefully you can see, there's not going to be any numbers on this in terms of what's given. Just the fact that these two segments are equal, or that that's a midpoint. And you're asked to find these two area ratios, the area of triangle 2, which is the small triangle, and the big triangle. And by big triangle, I mean this entire thing. The second part of this, when you really need to do this in order, find the ratio of area 1 to area 2. Area 1 to area 2. You almost always want to think of this first by trying to find a scale factor. So because these are similar triangles, you got parallel lines, you got similar triangles, you can compare these triangles with a scale factor. You don't need numbers to get that. If you called this 10 and this 10, your scale factor would be 10 to 20 or 1 to 2. That might be kind of obvious if you made up any numbers. This is 3, that means the whole thing would be 6. That's a 1 to 2 ratio. A lot of people will write that down for the answer here. It's a 1 to 2 ratio for the areas. Think about what you do at a scale factor to get an area ratio. It's not just a 1 to 2 ratio. And even look at the drawing. If you think of this little triangle, this is not this is not half of this entire thing. It's a fourth of the entire triangle. And again, that comes from squaring the scale factor. If you look at it, that kind of makes sense. One of these little triangles fits here, one would fit above it, one would fit to the right, and one would fit, kind of flipped over right up, kind of up and kind of diagonal to it, to the hypotenuse there. So think about this. I already led you in the direction of this one. This is a fourth of the entire thing. If this little triangle is a fourth of the entire thing, how much does that leave for this trapezoid space, this area 1? This is a fourth of it. I think it might be obvious that this must be 3/4 of it. So it's kind of like saying this is 75% of the whole thing, and this is 25%, and now I want you to compare those two things. Compare 75% to 25%. That's a 75 to 25 ratio, or a 3 to 1 ratio, which is what we're looking for here. Now, if you're confused by that, another way to think of it, area 1 comes from subtracting this triangle from the bigger triangle in terms of space. This entire space, subtract out that little triangle, and you get 4 minus 1. Again, I'm using these as sort of these ratio of areas on here. Subtract those two and you get that 3 to 1 ratio. And like I said, these are not actual areas. I don't know if I said that enough. These are not actual areas, but they're ratios of areas. I could put like a 3x to 1x ratio on here, or 3a to 1a. There's ratios for areas. And the last question on here, which is kind of obvious, the reason I have this though is some people say area 1 to area 2 is a 1 to 1 ratio. Well, that'd be kind of silly to think that way because they aren't even the same shape. This is a trapezoid and this is a triangle, so there's no way they could possibly be similar. Hopefully that makes sense. Give you a minute to kind of put that into your own words, and I'll pause and go to the next problem here. If you're ready, you can start that one. In a minute, I'll be back on part 3.